Awesome. And then, so to welcome everybody to this week's Exo-Webinar. I'm Zach Berta-Thompson. As we start every week, I emailed or Slacked somebody 2 hours ago asking them to share something that's making them happy this week. And Nestor very kindly responded to that call. Let's go ahead and go over to Nestor Espinoza. What's making you happy this week?
All right. So I made a very small presentation, of course. What's making me happy this week? So there's two things, all related to movies and videos. First thing, of course, that it's making me happy related to videos is that I'm now a TikToker internally with my family, but really it's my daughter who is the main character of all this crazy video sharing. So yeah, we've been knocking down some toys. No toys have been, injured with this one, but this is just for, a small kind of movies. But the really big thing that I wanted to speak about today, in which Mercedes is involved, is in a special movie actually, in which we were part of, that made it to Amazon Prime. So this is called Cielo. Cielo is a documentary about the sky, and in particular about Chilean skies, in which Mercedes, myself, and Stefan Udry as well, with ESO instruments, participated in. But the documentary is really beautiful in terms, the scenery that you can see. I mean, for those of you that have the privilege to see the skies in northern Chile, they're, breathtaking. And here, the scenography, the shots that they made to the sky, they're just beautiful. But the documentary, it's really, kind of Alison's journey into trying to speak with different people that have experienced it, have interact with the sky in different ways. And we're kind of the scientists in this narrative. There's also a couple of algae collectors that they also have a connection with the sky. And there's like different stories in this. The movie is not that long. It's 1 hour and 20 minutes or so. And I think our appearances with Mercedes and the appearance of Stefan, it's like, 20 or half an hour of the movie. It's really interesting. So yes, it appeared in Amazon Prime, so it's not free, of course. Sorry, folks. But you can get together and maybe do a watch on this. So you can go either to the website of the movie. So as you can see here, we appear as starring people here. So this is like our road to Hollywood, really. We can put in our CVs, I think, that we starred a movie or something like that. So just to give you a really small preview. So here's, for example, it's a shot taken from the movie, just Mercedes and I just staring at the sky, speaking about how big the universe is. But there's also funny moments. Why this warms my heart? It warms my heart in several ways. So one, Chile, where I come from, and anything related to Chile always warms my heart. My colleagues that might be here, they know that I just speak about Chile every time we meet. But also, the interaction that we have in the observatory and with Mercedes, which, the relationship that we have with Mercedes is kind of special because it's not only science, it's like a friendship going on. And so we have these really cool interactions in the observatory. So we were doing transit spectroscopy. Actually, the WASP-4 data that in the paper that we just published last year, I think, it was taken here. But it's a lot of things together. So I just recommend watching it, have a look at it, have fun at it. I am play some guitar in it, so that's the fun part as well. So yeah, that's like a surprise that I got this week on this that I wanted to share with you all.
Awesome. Thank you, Nestor. I'm so delighted I have something new to watch. This is going to be great. I look forward to the guitar.
Cool.
All right. Well, I guess we should. All right. We'll applaud for you a little bit now, but mostly Thanks. For after we watch the movie and see your starting performance and Mercedes.
Thanks.
Okay. So to get started with, before we get started with our talks today, I want to remind everyone to, just for trying to help everything run smoothly, please try to keep your audio muted unless you are actively talking or clapping. And then please feel free to have your video on or off. And then to ask questions, you can either add them to the chat like during the talk, or use the raise hand feature, or add your name to the chat at the end of the talk, and we'll call on you to ask it. We've instructed our speakers to ignore things that are going on in the chat. But if there's something like we can't hear them, then I'll interrupt them and let them know. And of course, as with all settings, please try to be friendly, courteous, and respectful of everyone here. So, okay, with that, oh, and then one more preface. I think many of you saw an email earlier today requesting you to submit abstracts for talks. We'd like to keep this series going through at least the rest of the year, and so we need more wonderful talks from you. So please go ahead and submit an abstract of something that you'd like to talk about that's broadly related to JWST or exoplanet atmospheres. Or encourage your any students or postdocs or anybody else you know to submit them as well. Okay, with all of that preface, let's please go over to our first speaker, James Kirk. So James, go ahead and share your screen, and then we'll let you take it away and tell us about HIP 41378. Thank you.
Thank you, Zach, and thank you to all of the organizers for giving me the opportunity to present today. So I am James Kirk. I'm a postdoc working at the Harvard-Smithsonian Center for Astrophysics. And today I'm going to be talking about recent work that I've done with my collaborators, including one who is now a movie star that I didn't realize before Nesta's talk, on assessing the atmospheric observability of the multi-planet system HIP 41378. So jumping in then to some background on this system. So back in 2016, Andrew Vanderberg and collaborators presented the detection of 5 transiting planets from K2 campaign 5 data around this bright V equals 8.9, J equals 8 late F-type star HIP 41378. Now, the inner 2 planets B and C are sub-Neptunes on periods of 15 and 32 days, and the outer planets D, E, and F only transited a single time each during the 75-day campaign 5 observations, meaning that the periods are only loosely constrained, but these are constrained to with uncertainties of around 30 to 100 days. And these periods are between around 150 and 300 days. And they also have long transit durations between 13 and 19 hours. So because of the long period nature of these outer planets and the brightness of the host star, this encouraged follow-up studies. And last year, Alex Santern and collaborators presented the results of 4 years of high precision radial velocity monitoring. And by combining these with astroseismic constraints and additional K2 and Spitzer data, they were able to constrain the mass and periods of the transiting planets, in addition to detecting an additional 6th non-transiting planet. And the main results of those studies are shown here. So you can see the masses and the periods that are constrained. And what they find is that planet F has an orbital period of about 1.5 years. And these masses that they find imply relatively low densities for these transiting planets, which in turn imply large atmospheric scale heights and large atmospheric signals, with this column here showing the transit depth per scale height in parts per million. Now on this plot here, I am showing different core compositions for these planets from the paper by Santern et al. And you can see that planet F sits way up here because it's its very low density of just 0.09 grams per centimeter cubed. Now this density is so low that it actually led Santern and collaborators to speculate that the planet might be hosting circumplanetary rings that are artificially inflating its optical radius. And this is a scenario that was investigated by Akin Sanmi and collaborators this year, who find that actually the K2 optical light curve can be equally well fitted by a planet with a radius of just 3.7 Earth radii as compared to 9 Earth radii without rings, but with rings that extend out to around 2.5 times the planet's radius. Now, this smaller radius combined with this fixed mass leads to a denser planet, which in turn gives a smaller atmospheric scale height and a smaller atmospheric signal, which has important implications for possible atmospheric characterization of this planet, as I'll discuss later on. So what might we hope to discover with JWST, and why might we study this system? Well, firstly, it's one of the best multi-planet systems for transmission spectroscopy. On this plot here, I show the transmission spectroscopy metric as defined by Kempton et al. In 2017 for all planets that reside in systems with more than 2 transiting planets and for which have measured masses and radii. Now, HIP 41378 is shown by the red squares here, and this has the 3rd highest median transmission spectroscopy metric of these systems considered, second only to the planets in the GJ 9827 system and to Kepler 51 as well, and above the TRAPPIST-1 and Kepler-11 systems. But the thing to note is that these planets extend out to much longer orbital periods than these other planets, which offers the opportunity to bridge the gap between the hot Jupiters that are typically studied and the gas giants in our solar system. Now, having 5 planets that form within a common disk is also very interesting to test the intra-system atmospheric diversity of these planets and to test things like the mass-metallicity relation of giant planets. So on here, I plot the 5 planets within the 5 transiting planets within the HIP 41378 system on the mass-metallicity relation of the solar system. And so you could see that this would offer a very interesting test of this relation out to lower masses than the solar system and testing planets that form within a common disk. And of course, we could also look at the C to O ratio and how this varies as a function of the semi-major axis. And finally, JWST would offer the opportunity to detect rings around planet F. Now, in this paper by Akinsami and collaborators, they suggest that in the far infrared, that the rings could potentially be transparent, which would lead to a much shallower transit depth observed in the far infrared as compared to the optical transit detected by K2. And it's possible that MIRI might be able to achieve this, observe this difference in the transit depth if the rings are indeed transparent. So with this very interesting system in mind, then our study, which is currently under review at AJ, sought to determine how many transits of each planet are needed by JWST to make a confident detection of their atmospheres. And by this, I'm ruling out a flat line at 5 sigma. This is what I mean by a confident detection. So the basic steps that we took were to create a grid of forward models for each planet using Platon, to apply JWST noise estimates using Pandexo, and then to iterate the number of transits to calculate how many are needed. And we assumed an optimistic mission length of 10 years for JWST. So going through each of these steps in a little more detail now, the first step was creating the forward models with Platon. And so we varied our metallicities from 0.1 to 1,000 times solar for the dense inner planets B and C, and up to 100 times solar for the less dense outer planets D, E, and F, and this scenario that planet F also has a ring. And we fixed the C to O ratio at the solar value of 0.53. And these 2 plots here show example opacity contributions for planet B at 1 time solar and planet F at 1 time solar. And because of the hotter equilibrium temperature of planet B, we see sodium and potassium in the optical, and in the infrared, we see absorption from water, methane, and carbon dioxide, potentially carbon monoxide as well. And at the cooler temperature of planet F, we see that in the infrared, the opacity is just dominated by methane, water, and ammonia. These 2 plots here are shown at a resolution of 100, but actually we generated all of our forward models at a resolution of 10,000. We assumed that the planet's atmospheres are cloud-free, but we did test the impact of aerosols by muting the spectra to 33% of their full amplitude. And we did this based on findings by Hannah Wakeford and collaborators last year, who found that on average, HST wide field camera 3 observations are typically muted to 33% of the expected clear scenario spectral amplitudes. And on this plot here, I just show an example for planet B showing the difference between the muted and unmuted scenarios. So therefore, in total, we had 52 forward models at a resolution of 10,000. So as I say, we then ran these through Pandexo, and we considered 23 instrument nodes in our study. We did not include the near-spec PRISM instrument because the brightness of the star HIP 41378 is about 2.5 magnitudes brighter than the saturation limit of PRISM. We considered each of these instruments at the native resolutions given here and at the lower resolution given in this column here. And I note for the H GRISMs of near-spec that this lower resolution could actually be achieved with the M GRISM, but with the advantage that the M GRISM does not have chip gaps. And however, for the purposes of our study, I don't think this has made a big difference. We adopted these noise floors based on similar studies in the literature, and then the number of groups for integration is resulting from the optimized function within Pandexo. So then we move on to calculating the number of transits required. And to start with, we took the ephemerides of Saturn et al. And plugged these into the NASA Exoplanet Archives Transit and Ephemeris service. Now, the really cool thing about this service is that it actually has the JWST target-specific observability windows built into its calculations. And so we're able to calculate how many transits would be observable by JWST within a 5 and 10 year time scale. For the inner planets, we find that potentially tens of transits would be observable. And fortunately for the outer planets, there are observable transits, although we find that for planet E, no transits are actually observable even within 10 years by JWST. So with these number of transits in mind, we then iterate the number of transits from 1 to 100. Now I go to 100 just out of curiosity to see how many transits would be needed. But of course, anything that requires more transits than I found on the previous slide, I rule out as being detectable by JWST. And then I calculate the chi-squared of a flat line for each number of transits. And this here shows an example for planet B with the near-spec G140H GRISM. In this case, 8 transits are needed to rule out this flat line at 5 sigma, and this is not achievable with 1 or 5 transits. Now, the important thing that we did was not only consider one single observation duration per transit, but we actually varied the observing duration as a function of the transit duration for each of the scenarios we considered. And so I plot here the time charged, and now this is calculated using the JWST APT software for nearest SOS. And this is per transit. So you can see that for a single transit, if you have an observing duration of 1.25 times the transit duration, then this would still constitute a median proposal for planet F, because planet F has such a long transit duration of 19 hours. However, for planets D and E, you could have a observing duration of 1.5 times the transit duration, and still that would constitute a small proposal. So we therefore had 52 forward models, 23 instrument modes, and 5 baseline durations, meaning that we had around 6,000 total models that we then iterated from 1 to 100 to calculate the number of transits required. And the first result that we find is that nearest SOS requires the fewest transits of all of the instruments that we consider. On this plot here, I am showing the median uncertainty on the transit depths across the system resulting from Pandexo. And this is shown as a function of the different instruments used at the different baselines considered, which are shown by the different colored lines, at both the native resolution and this lower resolution. And you can see that nearest SOS has the highest precision as it has the lowest, the smallest uncertainty on the transit depths. So taking nearest SOS then as a representative example, I can then plot the number of transits that are needed for each planet, assuming observations with nearest SOS that have been to a resolution of 100. On the y-axis here are the number of transits needed for a 5 sigma detection, and this is shown as a function of the observation duration. The different colored bars indicate the different metallicities considered, which are shown in this legend down here, with the open bars showing the scenario that the amplitudes of the spectral features are muted to 33% of the clear full amplitude features, and the clear full amplitude features are shown by the solid bars. The dashed horizontal lines in each case show the total number of transits observable by JWST in a 10-year baseline. So a couple of immediate things to note is that muted atmospheres will be very challenging to detect with JWST and will often require tens of transits to be stacked, and in some cases may require more transits than are actually observable in a 10-year mission length. However, the good news is that if the spectral features are not muted and these atmospheres are clear, then JWST can often detect in a single transit, and at most a handful of transits, these atmospheres with a high degree of confidence. Now, the point about the baseline is a very important consideration, especially when we're talking about long period planets with long transit durations. And probably as expected, we find that the total number of transits decreases as you increase the observing baseline per transit that you observe, but the gains actually decrease. So what we see is that by increasing the observation duration per transit from 1.25 to 1.5 times the transit duration, this on average results in 34% fewer transits that are needed to be observed. Extending this to 2 times gives a further 18% gain, and then we see a 7% gain and a 4% gain if you go all the way to 3 times the transit duration. And in particular, for something like Planet D, you can see that 2 times the transit duration would actually be enough in most cases to detect the planet's atmosphere from a single transit. And there's not actually much gained in extending beyond this. This is particularly true for Planet F, where we see that for all atmosphere scenarios we consider, actually a single transit at 1.25 times the transit duration would be enough to detect all of the scenarios we consider. And in fact, this would save you about 33 hours of observing time as compared to a 3 times the transit duration observation, which is not actually a crazy amount of time to spend for transmission spectroscopy observations. So I emphasize that the observing baseline is a very important consideration when observing long period planets in particular. But this is very encouraging for studies of Planet F. However, if Planet F does have a ring shown in this panel here, you can see that it will be very difficult for JWST to make a confident detection of the planet's atmosphere, even if it is able to detect the presence or absence of rings. And in this case, you would need 3 times the transit duration to detect a 1 or 10 times solar metallicity atmosphere, and only by stacking 3 transits. And if the atmosphere was further muted by clouds, for example, this actually would not be able to be detected within JWST's mission length, which we take to be 10 years. This is also true of the 1,000 times solar metallicity atmospheres of Planet B and C, where in the case of Planet C in particular, we predict that JWST would not be able to detect its atmosphere if it is 1,000 times solar. So just to emphasize here, the fact that Planet F you could save 33 hours of observing time if you only used 1.25 times the transit duration. So in summary then, HIP 41378 is one of the very best multi-planet systems for transmission spectroscopy, and we've conducted a study of how many transits are needed of each planet to make confident atmospheric detections. And we find that nearest SOS requires the fewest transits of any instrument to make a confident detection. And we also show that the observing baseline per transit must be considered, especially when you are observing long period planets. We find that for this system in particular, that clear atmospheres will be relatively easy to detect, but muted and 1,000 times solar metallicity atmospheres may be uncharacterizable in JWST's lifetime. So I'll stop there and gladly take any questions. Thanks for listening.
Awesome, thank you, James. All right, I will go ahead and please, raise your hand, use the raise hand feature if you have any questions, or feel free to type something into the chat as well. I saw, let's start with Tom Green, who raised his hand. Tom, go ahead and unmute yourself and ask your question.
Great, thank you, Zach. Thank you very much, James, for a great talk. I was wondering if you gave any thoughts into sort of the strength of atmospheric features versus wavelength using various haze models, and to sort of assess how different wavelength observations might of different modes might compete with the nearest SOS.
Hi, Tom. Yeah, that's a very good question. So by sort of assuming this blanket uniform muting to 33% of the full spectral features, we're essentially treating any aerosols as like a gray opacity source. And that is not necessarily the correct way to apply or to think about aerosols. Like with Peter Gower's recent work, you see that towards the mid-infrared, potentially these aerosols would be less optically thick, and maybe MIRI in that case might be a better instrument to use. However, it's also possible that, particularly for planet F, that even a 33% muting of the atmospheric features is not actually conservative enough. And for systems like planet F, Jessica Libby Roberts showed recently in a study of Kepler 51 that the superpuffs in that system actually show almost completely featureless near-infrared spectra. And in that case, then it would be possible that that featureless spectrum could extend out to longer wavelengths too, although there have been other studies suggesting that that's not true. So yes, I have thought about it, but we've not actually applied any more sophisticated haze models.
Thank you.
Thanks. Joseph Linden, do you want to unmute and ask your question? Or I can read it here if you don't want to.
I'll unmute, sure. Do you know of a good way to investigate if an exoplanet has rings? You allow for the possibility that planet F has rings because it could account for the lower apparent density, but could other planets have rings? What impact would that have?
Do you mean other planets in the system?
Sure.
Yeah. So so the reason that these rings were invoked was to try and explain this very unusually low density of this planet. And the idea is that in the optical, that these rings are leading to a deeper transit than would be observed if you were just observing the planet itself without the rings. And it's possible that these rings would have a wavelength dependence, and in the mid-infrared, that these wavelengths could be optically, these rings could be optically thin, and you'd be able to detect a difference in the transit depth between the mid-infrared observations with MIRI and the optical observations with K2. I think that it would be very interesting to observe these rings in the infrared to look for specific spectral features which may be caused by the rings as well. That's not something that we have actually looked at specifically, though. I'm not sure if that answered your question.
It guides me.
Okay.
Cool, thank you. I have, Nestor, go ahead, ask your question, and then we'll move along to our next speaker. And then I'll add that after, yeah, go ahead, Nestor.
Cool. Thanks, James, for this talk. One question I had is that this conversion from optically thick to optically thin in the IR, like mirror wavelengths, is not most likely not binary, right? It has to be like a continuum, kind of like this should be observable also like in a transit spectrum, so to speak, like a multi-formed version, of course. Have you explored this? Has anyone explored this?
Are you referring to the rings in particular?
Yeah, so right. So you said like if you observe at Kepler wavelengths, yes, it's like big thing. Yes. But if you observe it at MIRI wavelengths, perhaps, those disappear and you only see the central part, like not the rings. But then that's not a binary conversion. It's not like you just go, over 3 microns and then whoop, the planet it diminishes to a small ball. It's most like a continuum.
Yeah. Well, I think that, there have been studies of Saturn's rings which show how like the spectra of the rings changes as a function of wavelength. It's possible that something similar would be happening for this system, although the actual composition of the rings would likely be different because of the difference in temperature between Saturn and these rings, which are presumably would not be icy. There was actually an interesting paper on Archive today, I forget who that were looking at the compositions of potentially dusty tails of exoplanets. And it's possible, in my mind at least, that you could have a similar scenario where these rings are dusty. And these guys have shown that for these dusty tails that you would be able to detect, as you say, like this varying sort of change in the continuum as a function of wavelength for different like dust compositions. And it's possible that the rings would show a similar thing as well.
Cool, thanks.
Awesome. Cool. All right. Well, let's thank James one more time. And Kristin, go ahead and get your screen set up to share. And I'll also add that I've asked both of our speakers to be able to hang around a little bit after the end of the hour too, so you'll be able to leave before the end of the hour. But if you have more detailed questions, you can stick around and ask them then. Okay, but so now go ahead and take it away, Kristin Showalter, to tell us about transmission color analysis. Thank you.
Thank you, Zach, and thank you for the opportunity to present today. I'm Kristin Showalter Sotzen. I'm an analyst at the Johns Hopkins Applied Physics Lab, as well as a PhD student at Johns Hopkins University. And today I'm going to talk about an APL-led effort to investigate the use of transmission color analysis for exoplanet characterization. I do want to give a quick shout out to Natasha Battaglia for all her help in advising this effort. As we all know, largely thanks to Kepler and TESS, the number of transiting exoplanet detections has increased dramatically in the last decade. And we typically use spectroscopic light curves to extract detailed information about an exoplanet's atmospheric composition and structure. However, these light curves usually require significant observation time on large telescopes to construct. So we wanted to look into the question of whether transmission color analysis or color ratios can provide the capability to coarsely characterize exoplanets using low resolution data, which could allow for smaller telescopes and or shorter integration times and facilitate the broad characterization of larger numbers of exoplanets. Color analysis has historically been used for reflectance spectra, and trends have been shown for both solar system planets and exoplanets in reflected color space. TROB 2003 showed trends for solar system planets in specific blue, green, and red filter combinations. Crow et al. 2011 showed that Earth has a unique color signature using specific filters from the EPIC HRI instrument. And Christensen Sutton et al. 2016 showed that modern Earth has a unique spectrum in reflectance color space relative to other worlds due to biogenic ozone and oxygen. Battaglia et al. 2018 built on these studies by analyzing the reflected light spectra for over 9,000 simulated extrasolar giant planets using a statistical approach over metallicity, phase angle, and cloud profiles. They focused on W-first-like filters in the optical and near infrared, and using multivariate analysis, they found correlations between color ratios and W-first-like filters for cloud-free planets. So they did find that those correlations were diminished once clouds were introduced. Given these trends that have been found in reflectance color space for solar system planets and exoplanets, and given the large number of transiting exoplanet detections, we wanted to investigate adapting the Battaglia et al. 2018 analysis framework for transmission spectra. For our simulated spectra, we are using the GOIL grid of ATMO forward models, as described in GOIL et al. 2018 and 2019. We're particularly interested in the question of differentiating super-Earths from sub-Neptunes. So we focused on a planet with a radius of 1.7 Earth radii and gravities of 10, 16, and 20 meters per second squared. We wanted to include a range of metallicities so that we can investigate the estimation of mean molecular weight for these planets, and atmospheric metallicity corresponds approximately to mean molecular weight. So we made sure to include a range for our metallicity parameter. We wanted to cover a range of wavelengths to make sure to capture any potentially significant atmospheric and biosignature features that are detectable with achievable instrumentation technologies. So our investigation covers a wavelength range from 0.2 to 30 microns with a resolution of 20. This gives us 104 filters and over 5,000 filter pair combinations for our analysis. The Battaglia et al. 2018 framework is open source and available on GitHub, and we only had to make a few fairly minor modifications to the framework for our purposes. We modified the interface that generates the filter set, and we also developed a script to parse the GOIL spectra into the pandas database format that the framework requires. And we modified the color-color calculation from a reflectance color metric, which is a difference in magnitudes and essentially a flux ratio, to the transmission color metric, for which we are using the average transit, the ratio of the average transit depth for the two filters in a pair. The primary tool in the Vitale et al. Framework is linear discriminant analysis, which is essentially an information content analysis that produces weighting coefficients for each of the analyzed variables that indicate the relative information content of each variable. In this case, our variables that we analyzed are our filter pairs. This figure from Vitale et al. 2018 shows the results from a linear discriminant analysis based on those weighting coefficients. And for this LDA, where they were attempting to classify planets by metallicity for a cloud-free sample with a constrained phase angle, we see that the LDA is able to separate those planets out as indicated by these distinct peaks in the linear discriminant values. Subsequently, they unconstrained the phase angle, and we can see that for the LDA, that separability is diminished as indicated by the broader peaks that are starting to have some overlap. So for our data, we organized our spectra into 7 different mean molecular weight groups, with the lowest groups representing or approximating Jupiter and Neptune, and the highest groups approximating Earth and Venus. And when we run the linear discriminant analysis on all of our data using all of our filters, we can see that our linear discriminants there is notable separability for the linear discriminants. We can see the different groups for the molecular weights. There is some overlap in the higher molecular weights, but they are still distinguishable. One of the other products of the linear discriminant analysis is a prediction for the mean molecular weight of a given spectrum based on the linear discriminant values and those weighting coefficients. And when we compare the predicted mean molecular weight for our spectra to their true mean molecular weights, we can see that there's a fairly high accuracy in that prediction. Here in this plot, the symbol size represents the prediction accuracy percentage. So one of the other metrics that we are tracking is allows for the molecular weight assignment to fall into a neighboring molecular weight group. And we're terming this the adjacent prediction accuracy. And so for the adjacent prediction accuracy, if a molecular weight prediction falls on either side of the true mean molecular weight for that spectrum, we are also considering that correct. Whereas for the true prediction accuracy, it's only considered correct if it falls in the one true molecular weight for that spectrum. So I've shown the results of the linear discriminant analysis for our data using all 104 filters, but clearly it's not going to be practical to use 104 filters spread from 0.2 to 30 microns. So next we had to figure out how to sub-select for a set of filters that we can use for our observations. So we investigated two different approaches to this filter sub-selection. First, we looked at those weighting coefficients from the linear discriminant analysis to see which filter pairs were most strongly weighted and therefore, according to the linear discriminant analysis, would provide the most information about our spectra. We also performed a Pearson correlation analysis between the filter pairs and the mean molecular weight to determine which filter pairs were most strongly correlated with the mean molecular weight. And in these plots here, I'm showing the top 3 molecular weight correlated filter pairs on the left and the top 3 LDA favored filter pairs on the right. We can see that while they're not exactly the same, they both fall more or less in the infrared, and both filter selections are triggering on known molecular absorption features, with the correlated filter pairs triggering more on the water feature at 6.5 microns, and the LDA favored filters triggering more on the CO2 features at 4.3 and 15 microns. So we have our 2 methods of filter down selection, but we also needed to know how many filters we need to achieve a given molecular weight prediction accuracy. So we investigated so we ran the linear discriminant analysis for different numbers of filters for both the LDA favored filter subset and the correlated filter subset, and we investigated the true molecular prediction accuracy as shown in the solid lines on this plot, as well as the adjacent molecular prediction accuracy as shown with the dashed lines. And we can take a couple of things away from this plot. First, we can see that based on the solid lines, for a true prediction accuracy, we would need more than 50 filter pairs for an accuracy of at least 80%. And 50 filter pairs is not particularly practical, so that's not looking particularly promising there. However, we can see that many fewer filter pairs are needed for an acceptable adjacent accuracy prediction of 80 or 90%. So fewer filters are potentially more tractable if adjacent accuracies are acceptable for the mean molecular weight estimates. We can also see here that the correlated filter pairs outperform the LDA favored filter pairs up until about 15 or 20 filters. So basically, for practical numbers of filters, the correlated filter pairs perform better. So for our subsequent analyses, we would likely go with the correlated pairs. This table shows some specific accuracies for the top 3 LDA favored filter pairs compared to the top 3 molecular weight correlated filter pairs for a couple different data subsets, because we wanted to take a look and see if we could identify any accuracy trends based on clouds or different temperatures. And what we found is that there's actually not very much difference between the data sets in the prediction accuracy, and that the accuracy, the true accuracy, regardless of data set or filter combination, is not very high, around 50 or 60%. But the adjacent correlation, the adjacent accuracy prediction for the top 3 correlated filter pairs for all of the data sets is 80% plus, more or less, which isn't too bad considering we're looking at using considering that this particular analysis was looking at only using 3 very specific filters, or filter pairs, I should say. Also worth noting is that the cloud-free data subset didn't result in significantly different performances from the other subsets. So clouds did not have a significant impact on the analysis. Since it's looking like the smaller number of filter pairs are perhaps not going to provide the accuracies that we would want for our molecular weight predictions, we also wanted to look at the prediction accuracies if we used James Webb and Hubble spectroscopy. So we looked at several instrument observing modes for James Webb, as well as the WST3 141 GRISM for Hubble. And what we found is that even using spectroscopy for James Webb and Hubble, that the true prediction accuracies are still low-ish, 60 to 80%, but the adjacent prediction accuracies using spectroscopy for these instruments is pretty high, generally 90% or better, with MIRI LRS and NIRIS SOS performing the best at approximately 98% prediction accuracy for those adjacent pairs. So accounting for solar noise considerations, we would expect NIRIS SOS to be the recommended instrument mode for estimating the molecular weight of an exoplanet atmosphere. In summary, our preliminary results do seem to indicate that transmission color analysis could be useful in distinguishing between low and high molecular weight atmospheres, which is promising for differentiating sub-Neptunes from super-Earth. Also, clouds do not seem to significantly impact the separability of these different atmospheres, with generally less than 5% difference in molecular weight prediction accuracy between data with clouds and data without clouds. This is more than likely due to the most correlated filter pairs being in the infrared, which is not as impacted by clouds. Also, NIRIS SOS is expected to be the recommended James Webb instrument mode to estimate an exoplanet atmosphere's mean molecular weight. And going forward, we will account for instrument throughput and SNR, which was not a consideration for this particular investigation. And we will also consider requirements for future instrument and spacecraft technology development. So thank you for listening, and I'll be happy to take any questions.
Awesome. Let's thank Kristin for an awesome talk. That was wonderful. Are there, so again, if you have questions, please use the raise hand feature or just type something into the chat. And I think we'll start off the bat with Daniela. Do you want to ask your question?
Sure, thank you. Hi, Kristin, that was really interesting. That was a really cool talk. I am curious to, well, now that I see your results, I'm really curious to understand what's the relationship between mean molecular weight and whether there's a correlation with both metallicity or the composition of the atmosphere. I'm asking this because my student is actually working on a complementary technique to predict variability. So, you know, if you can predict molecular weight and I can predict clouds, we can predict the whole atmosphere. So that'd be cool.
Okay, so the question is whether there's a correlation between metallicity and, or between molecular weight and atmospheric composition?
Yes, because I wonder if your technique could also predict not only the high molecular weight atmospheres well, but also the metallicity of the object we're looking at.
So we would expect the mean molecular weight to provide an indication of the overall composition of the atmosphere. Clearly, if it's a mean, and then we're looking at an average, and and we'd only be looking at transmission spectra in particular. We're looking at a smaller region of the atmosphere, so we may not necessarily be capturing potential changes due to the structure of the atmosphere. But we are assuming that mean molecular weight, that larger molecules are going to raise or lower that mean molecular weight based on the composition of the atmosphere. And like I said at the beginning of the talk, we're kind of taking the metallicity to be I can't say it's not a proxy for mean molecular weight, but they're correlated. The higher the metallicity, generally the higher the molecular weight. So the relationship isn't linear, but they do correlate that way.
Okay. Yeah, that's interesting. Thank you. I think there's potential for connecting the dots.
I think so.
Yeah.
I'm going to take the chance to ask a question I have, which is, and it's possible that your answer is we just need more precise data, but are there existing data sets that you can apply this to? I'm thinking particularly of, there was a nice data set that was compiled by Sherry Guo and Sarah Ballard, looking at the ratios of transit depths in the Kepler bandpass and the Spitzer bandpass. And I know those aren't the like optimized filters that you explored here, but can you learn anything by looking at those existing data?
That is an excellent question, Zach, that I've been thinking about for a little while, actually, as far as a follow-on to this analysis, is can we start applying this to actual data sets? That was one reason why I wanted to look at the James Webb, which obviously that's not an existing data set that we can look at yet. And one reason why I included the Hubble 141 GRISM to see if that accuracy might be something worth exploring, since we have so much Hubble data on these planets. So that is something I'm thinking about. I don't have a solid answer yet, but I'm hoping to soon. It is something I'd like to look into a little more.
Cool, thanks. Nestor, would you like to ask your question, maybe compressing it slightly from?
Yeah, of course. Chat? Yeah, I had a train of thought in the chat, just don't look at that. So first of all, really cool talk. One question I had was related to the fact that the clouds don't really impact on the accuracies, and I was wondering if that's because I would think that naively that would depend on noise levels. So I just wanted for you to maybe explain a little bit on what the sample that you selected for the possible planets was. Did you add any noise levels and realistic noise levels in the different targets that maybe JWST could observe? And also if the accuracies that you gave were from just one simulation or several simulations with noise. And if that's the case, I would expect maybe that the cloudy one would give you a larger variance on those accuracies, because the accuracies have error bars associated to it. So that was basically the question. If you can comment on that.
So our data set is, we didn't include any real noise sources, certainly no instrument noise, and not even really solar variability. So this really is kind of a best case scenario as far as the color analysis, but we wanted to start there because if it doesn't work there, it's not going to work anywhere. So that would be something that we want to do going forward, is to include more noise sources. And I agree with you that the impact of the clouds will increase those variances once we start including those noise sources. And I think it was largely because the most strongly weighted and correlated wavelengths for our filter pairs were in kind of the near and mid infrared, was why we weren't seeing a lot of impacts from the clouds. And there was a little bit of an impact. It wasn't exactly the same. The impact wasn't zero, but it was just a little less than I was initially expecting until we started investigating which wavelengths the analyses were triggering on. And they're wavelengths that are not as impacted by clouds when we don't consider additional noise sources.
I see, thank you.
Cool. All right, well, let me, in a minute, I'm going to ask you to unmute your microphones and give a round of applause for both of our speakers. But then I'll also say that we'll call that the end of the talks for today, and we'll kind of transition over into the people gathering up their mugs and laptops and stuff and hanging out for a little while afterwards if you want to continue to talk about any of this. So please go ahead and unmute, and let's give another round of applause to both our great speakers.